Welcome to the CFE Media and Technology Education Session, examining plant floor network security and protection methods. I'm your moderator, Mark T. Hosky with CFE Media and Technology and Control Engineering. In keeping with our CEP policy, please take some time to read the quality assurance slide. This session is designed for technicians, engineers, and professionals in information technology and operational technology areas seeking ways to help implement defense-in-depth methodologies to strengthen their network defenses. Here's a list of the learning objectives for today's presentation. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes within the session, click the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. Please remember that the live session will be followed by a question and answer session after the presentation ends. An industry expert will answer viewer questions live, and those questions and answers will be archived with the session. You can see the Q&A details in the Meetings tab on the left side of the screen. Here's some information about obtaining an approved PDH for today's session. Today's speaker is Charlie Norris, Senior Product Manager with WAGO. I'm your moderator, Mark T. Hosky, Content Manager, CFE Media and Technology and Control Engineering. Charlie Norris is Senior Product Manager for Automation at WAGO Corporation, located in Germantown, Wisconsin. WAGO's parent company, located in Minden, Germany, pioneered cage clamp spring pressure connection technology and uses it in its extensive range of interconnect, interface, and automation solutions. For those taking this course, please see the Q&A details in the Meetings tab on the left side of the screen. Now we'll have a brief commercial, followed by Charlie's presentation.
WAGO's family of lean-managed switches are designed to meet the needs of the ever-changing landscape of industrial networking. Our devices meet security and redundancy requirements for IT networks while remaining easy to maintain by plant floor technicians. To learn more, go to www.wago.com/us/lean-managed-switches.
Welcome. Thank you, Mark, for that introduction. In this session, I will start with an overview of strategies for cybersecurity on the plant floor and provide you with some resources for further study. As you will learn, there are multitudes of processes and technologies to help industrial manufacturers secure their plant floor. However, in this session, I will only focus on plant floor networks, as this is where engineers get a lot of bang for their buck. For a small investment in lean-managed switches, network security can be greatly boosted, and we will explore many features of managed switches that can help secure your Ethernet networks. So let's get started. Well, as you know, Ethernet has been prevalent on the plant floor for over 2 decades. When control engineers started using Ethernet-based field buses, they were thrilled by the benefits that this technology offered. Increased communication speeds, system performance enhancement, and less wiring were just some of the benefits. But at the dawn of the plant floor Ethernet-based networks, cybersecurity was not a concern for most engineers. However, today, critical infrastructure is under constant attack from bad actors looking for money or seeking political gains. These are recent headlines of just a few examples of cyber hackers that were able to breach defenses of critical infrastructure via remote connections. So today, controls engineers still can enjoy the benefits of Ethernet-based field buses, but they must add network security to their design process. So the US government has lots of information on cybersecurity. However, I want to refer you to these two documents. Homeland Security has a document for recommended practices on improving cybersecurity using defense in-depth strategies. This document provides a high level strategies for protecting industrial infrastructure. This document is a great reference for anyone who wants to learn more about multi-tiered approach to cybersecurity. And another government publication we're studying is the National Institute of Standards and Technology, or NIST, Guide to Industrial Control System Security. This document is geared more to automation topics for controls engineers. I would recommend these documents to you. You can download them for free of charge off of their respective websites. Oh, in both of these documents I just discussed, they recommend using defense in-depth strategies for protecting critical infrastructure. Defense in depth is a holistic approach to protect plant floor assets from cyber hackers. This strategy employs multiple layers of monitoring and protection so that in the event of a breach of one layer, a secondary or tertiary layers are there to limit the effect of the attack. In this presentation, I will only focus on a few levels of the defense in-depth strategy. It is important to remember that these strategies are not the only ones that controls engineers to think about. Engineers must work to develop the multiple layers of defense. In the Homeland Security document, I think this is table 2, you will first find this list of defense strategies that should be considered. I will discuss some of these technologies that can be implemented in the ICS network architecture and the network perimeter security levels. So let's start off by looking at two common types of Ethernet switches that you will find in control systems. The one on the left is an example of an unmanaged Ethernet switch. There is no configuration necessary with these switches. It's just power them up and plug in your devices and everything starts communicating. However, the downside is that there's not many ways to secure these switches. You can lock them in a control cabinet to limit physical access, but that's about all you can be done. Now, the diagram on the right uses managed switches. Managed switches are also used in industrial applications for connecting Ethernet devices, but they offer features that users can increase system performance, improve availability, enable network diagnostics, and of course, help improve network security. These switches require engineers to configure them for their specific applications. Now, managed switches have been used by IT professionals for decades. However, today, markets offer lean managed switches that are optimized for use in industrial control networks. These switches are hardened for continual use on the plant floor. They are also loaded with networking features that are commonly used by controls engineers. They do lack a lot of features that IT professionals use for business or server-based networks, but that means that they are lower cost than a fully managed switch, but they are still geared for industrial control systems. Most lean managed switches can be easily configured using your favorite web browser. They can be easily set up. So we will look at some of their capabilities and how they can be configured to help improve your network security. So before I begin, I'd like to explain a little bit at a high level what an Ethernet switch does. As we saw on the previous slide, Ethernet switches are used to enable communications between devices. But how does this switch do this? A basic function of Ethernet switches is to receive a message from one device and forward the message to one or more devices. These messages are packaged in an Ethernet frame. This is a standardized message described in the IEEE 802.3 standard. This frame has 7 data sets. As you can see on the left, the preamble is the first of the data sets, and it's used to synchronize the timing of the message with the device that's reading it. The SDF indicates that the next section is really the beginning of the message. Then comes the destination address for the message, and this is in the destination's device's MAC address. Then comes the source address of the message, and then the message itself is followed up by a CRC that is used to determine if any part of the message can be or is corrupted during transfer. So as you can see, that if a hacker has access to the Ethernet frame, they can gain a lot of information. They will know the address of at least 2 devices on the network, and then they can use that information to try to gain access to those devices. Or they may try to inject Ethernet frames into devices with harmful instructions. They're also able to read the message in the data section. This may be some critical information that could be used for malice intent. So when switches are powered up, they communicate with all devices that they are attached to. They ask what are their MAC addresses and what are they attached to. The Ethernet switch then stores this information internally in its MAC address table that lists the MAC address of each port is connected to. And when a connected device wants to send a message to another device, the switch will forward the message out the port it knows the destination device is connected to. So, for example, if the device on the left wants to know what the temperature is, it will send out a request. This request moves from switch to switch until it reaches the destination device. The destination device then will reply with a temperature following a reverse path through the network. So you can see cyber hackers may use different methods to either monitor critical data that they may want to inject false frames in the network, or they can disable the entire network. Therefore, it is the goal of a controls engineer to keep unwanted users off the network. So let's look at a very simple way to prevent an attack on a network. In many cases, engineers specify an Ethernet switch that has more ports than they will use in the design. Of course, this is a common practice as engineers know that projects change and more devices may be added, or they may be thinking about future expansion. In any case, these unused ports are at risk. Someone can physically connect an unwanted device to the extra port and gain access to the entire network. So a simple way to prevent this is just to disable unused ports. Using the web-based configuration in a lead managed switch, this is easy to do. On the left side of the screen is a screenshot of a web-based port setup. And you can see that port 4 has been disabled by the administrator. So this port will be inactive, blocking any unwanted access. And if in the future the port is needed again, it can be easily enabled by the administrator. Well, here's another example of a common control architecture. Many times remote devices like this distributed Modbus coupler shown here has a 2-port Ethernet switch on the device. A savvy hacker may try to connect to the unused port to gain access to the network. So what can be done? In this case, the lead managed switch has the ability to limit the number of devices that are connected to the port. In this section, in this screenshot of port security of the lead managed switch, you were able to set the number of MAC addresses that the switch port will connect to. In this example, port 2 is limited to only 1 MAC address. Therefore, if the hacker connects to that spare port on the Modbus coupler, the lead managed switch will not accept messages from the second added device, helping to keep your network more secure. Well, here's another possible scenario. What if the attacker unplugs a known device on the network and plugs in an unwanted device in the same port? This may be a way to gain access to the network. The breach may not be noticed until the disconnected device is needed, but this may be time enough for the hacker. A way to prevent this using a lean managed switch is to use advanced port settings. If this setting is enabled, when a known device is offline, that is, it's unplugged from the switch will go into, or the port will go into a shutdown mode, and the port will be disabled, will disable itself. It then would need to have an administrator with access to the lean managed switch to set the port back into normal before it can be used for communication. This will prevent someone from switching out of known devices for unknown device. So in this example, in the screenshot, port 16 has been shut down because the known device was unplugged. The hacker can plug into the port, but it's disabled. All right, and also in fully managed switches and in lean managed switches, it's very common for them to have a security access control list. This is commonly known as a firewall. Firewalls are used to allow or disallow devices to communicate with each other. Therefore, rules must be set up for the switch to know what devices are allowed on the network and what devices can communicate with each other. In this example, the PC has full access to the PLC processor in the lower right of the diagram. This is because this drop state is set to disabled in the ACL rule. But in this example of the ACL, the drop state has been changed or set to enabled, and therefore communications from the PC to the PLC is blocked. Now, controls engineers can set up multiple communication rules to allow or disallow communication between devices. This can help with cybersecurity, as unwanted devices will not have access to the network. You may be asking yourself, well, how can I limit access to the managed switch or lean managed switch itself? Well, these types of switches offer the user the ability to limit access to itself via service control configurations. For example, this screenshot shows communication ports that access the managed switch or lean managed switch, and they can be enabled or disabled. These can be set up per your own application so that you can enable only the types of communication you're planning to use, so that hackers have a reduced chance of gaining access to the configuration of the switch. All right, and some applications may call for more advanced methods of network security. So IEEE 802.1x is a standard for device authentication security. In this type of setup, there is a radius server on the network that holds a lookup table of allowed devices and their related passcodes. So when a device called a supplicant, and in this case, an example of the PLC in the lower left, is attached to the network, it must request communication rights. The lean managed switch acts as the authenticator and will ask the server if this device is allowed on the network. When the server gives a green light, then the switch will allow the PLC to communicate on the network. So setting up an 802.1 network takes some planning, but setup via the setup screen and the web-based configurator or lean managed switch, the process is straightforward. And this is an example of a setup screens for 802.1x authentications. As you can see, it's a bit more involved, but with careful planning, the process can be completed successfully. One method in the defense in-depth strategies discussed earlier is to separate your network into zones so that if a hacker gains access to one area of the network, they can't have access to the entire plant. Now, it may be inconvenient to have dozens of separate physical networks on your control system, but you can use virtual local area networks or LANs to do the job. In a LAN, the Ethernet frame is modified with an extra data set. In this data set, a LAN ID is added so that messages of the same VLAN can communicate together. However, VLANs of other IDs cannot communicate even if they share common hardware. Let's take a look at that. So here is an example of a network that shares common hardware but has 3 different VLANs. In this case, any device on VLAN 1 can communicate with each other, but devices on VLAN 2 or VLAN 3 do not have access to VLAN 1 devices. So a nice feature of VLANs is that it's possible to have a trunk line to connect 2 switches together. All 3 of the VLANs can use this common trunk, so it's not necessary to use a trunk line for each of the VLANs. And using VLANs can help separate networks for security purpose, but they can also enhance network performance by breaking up message traffic on separate virtual networks. Fully managed and lean managed switches typically offer controls engineers to build up or set up multiple VLANs. Another way to limit access to a network is using virtual private domains. Now, this is similar to a VLAN, but is enabled on the lean managed switch itself, and that the Ethernet frame is not modified. So, for example, it is possible to zone the lean managed switch so traffic can be assigned by port number. For example, you may only want a device on port 7 to communicate with a device on port 8 and no other ports. From this screenshot of the configuration, you can see using a matrix, you can assign what ports can communicate with each other. And in this example, ports 7 and 8 are isolated from the rest of the ports. All right, if we are concerned about hackers getting data, how can we protect Ethernet communications that are in unprotected areas like between 2 buildings on a campus, spanning multiple floors in a rented office, or in a remote setting? Well, controls engineers should consider encrypting the Ethernet communications in these types of locations. Encryptions help ensure that attackers can't monitor data or inject unwanted messages on the network. But how can this be done when I use common devices like PLCs and drives that do not have encryption capabilities? Well, let's take a look. Well, encrypting data in industrial environments can be done with secure switches using Media Access Control Security, or known as MACsec. This is an IEEE standard per 802.1ae. Using MACsec-enabled switch, encrypting any Ethernet message is easy and generally low cost. MAC security is point-to-point. One switch will encrypt the data, and the other is used to de-encrypt the data. So in this diagram, we have 2 controllers that house common control devices like PLCs, HMIs, and VFDs. The top Ethernet ports has features like a lean managed switch, so the devices do not need to have an encryption capability. The control devices can communicate with each other without the need of encryption. The bottom ports of the switches are able to encrypt data. The Ethernet traffic that leaves the security of the locked control enclosure is encrypted, so that even if a hacker gains access to the cable, they cannot decode the messages. Also, the encryption messages are synchronized, preventing hackers from injecting messages into the networks. MACsec encryption is done at the hardware level, so there's nearly no latency added to the network traffic. Setup of this type of encryption is very simple using the switch's web-based configuration. So MACsec is a secure and low-cost way to help improve your plant floor security. As I discussed before, the advantage of using a managed switch over an unmanaged switch is the ability to configure it for different functions. As we just reviewed, a key benefit of the lean managed switches is the ability to invoke security features to help keep cyber hackers off the network. But other advantages of using these types of switches is to increase network performance, improve network availability, and add network diagnostics. So if you choose to use lean managed switches to help with security, you should take advantage of these other features as they come with most managed switches. So let's look how these other networking features can help you with day-to-day activities on the plant floor. So first, let's start with diagnostics. Lean managed switches offer simple to use dashboards like the one shown here. You can use your favorite web browser to view this information, and these are usually monitoring only screens, so there is no need for a password. This offers the advantage that anyone has access to this information. So if there is a problem on the plant floor, technicians or even machine operators could use this dashboard as a fast troubleshooting tool to check the network. Everyone can recognize that the ports on the bottom of the switch are working properly. They're all in green. But the ports on the top are showing up as red and yellow as an indication of a problem. If the port is red, this means that there should be a device plugged into the port and it's not there. The cause may be that the port was unplugged, or another possible reason is that the device on the other end has lost power. This is a great start to tracking down a potential network problem. I will also note that the port showing yellow indicates that a device is plugged into that port, but the switch is not set up for the device. So it may be possible that the device was unplugged from the top port and then by mistake plugged into the port below it. But it would be really nice to have more information about how the network was intended to be set up. Let's look at a topology map. The topology map can also be viewed using a web browser. And this type of diagram will show the viewer how the network should be set up. The screenshot on the left shows the network setup. The control engineer set this up by configuring the topology map with all the connected devices. Now, this may sound like a lot of work, but many Ethernet devices today are equipped with LLDP, or Link Layer Discovery Protocol, which is an IEEE standard that allows connected devices or stations to send their information to others on the same LAN. If supported on the device, information such as descriptions and addresses are included automatically and displayed in the topology map. If the device does not support LLDP, the control engineer can manually set it up in the Lean Managed Switches web-based management. But as you can see by the screenshot on the right, that the port that was showing up red on the dashboard is connected to a camera. And the red line indicates that this connection or communication link is down. This provides technicians with information to quickly track down a problem. Without this map, you can imagine that technicians may spend a lot of time trying to figure out what is the problem with the equipment. And perhaps the camera is really the last thing that they check. So a topology map can be used to help reduce downtime. Another technology you may want to leverage is SNMP. IT network administrators have tools to view the health of network devices themselves. And this technology is also available in industrial lean managed switches. SNMP, or Simple Network Management Protocol, is known widely across the switch industry and is used in network management systems to monitor network attached devices for conditions that warrant attention, usually by the network administrator or a controls engineer. This information can help users identify specific problems with the switches or the network. For example, event traps such as power failure or backup power supply systems, or overvoltage or undervoltage, loop detection, and traffic alarms can all be reported. A SNMP manager can be used to monitor all the switches on the network to identify any potential problems. This tool also helps reduce downtime by either being proactive in correcting an issue before it causes a shutdown, or to quickly track down an issue during an outage event. Now, setting up SNMP is very straightforward using a web browser configuration tool. In this screenshot, you can see that a controls engineer can simply use checkboxes to configure what types of event traps they want to be reported over SNMP. This is simple type of configuration, helps speed commissioning of any network. Next, I would like to discuss other ways to help improve your control network. But first, let me define some terms I'll be using. So Ethernet messaging can be sent out in several different ways. The most simple type of communication is called unicast. This is where one sending device is transferring a message to a single receiving device. However, to optimize network bandwidth, some applications need to have the sender transfer messages to multiple receiving units. So this uses multicast. As you can see, this is more efficient than sending the same message to one at a time via unicast. And in some applications, the single sender may want to send a message to every device in the network, and this is called a broadcast. In some situations, a packet may arrive at the switch and the device doesn't have any information about the destination of the message. So this would be classified as a destination lookup failure. There are applications that can use all the communications as their normal function. But if there are too many devices on the network using these methods, you could have a broadcast storm. Or in other cases, a hacker may be trying to disable the function of the network by injecting lots of broadcast messages. So a tool that can be used to help improve availability in the network is called storm control. Storm control is used to limit the amount of traffic on a network. A traffic flooding situation occurs when a network is overwhelmed with constant broadcast or multicast traffic, which may lead to a loss of packets, or in the event of a network shutdown. Storm control protects the switch from flooding packets, including broadcast packets, multicast packets, or destination lookup failure, or DLF. So using storm control function, a threshold value can be set and monitored in packets per second. And this threshold value will not allow incoming packets to exceed the set limit by discarding exceeding packets. As seen here in this web-based configuration tool, each port can have a unique broadcast, multicast, or DLF setting to limit the number of packets coming into each port. Using a tool like this can help reduce any downtime by protecting the network from data storms. In some applications, controls engineers may want to set an alarm if traffic flooding or storm occurs. In lean managed switches, controls engineers can set up alarms by port to trigger if a set port is exceeded. In this screenshot, you can see that the threshold can be easily set up to trip an alarm via SNMP, or in some switches, an alarm relay can be enabled as an indication of a flooding event. These alarms can be helpful for controls engineers to identify if a device on the network should be configured differently to reduce the network traffic, or it could indicate someone is injecting messages on the network with the intention of causing a shutdown. So now, next, let's explore IGM snooping. In many networks, a single sender needs to communicate with multiple receiving devices. As we discussed, this is multicast communications. Several industrial field buses, such as Ethernet IP and Profinet, use this type of communication. For example, a PLC may need to send information to drives, HMIs, and distributed I/O. These field buses will use multicast messaging that goes to all the devices on the network. However, this is a lot of traffic, and many devices on the network don't need these messages. In order to help reduce network traffic, a technology called IGMP snooping, or Internet Group Management Protocol snooping, is used. In its basic form, the lean managed switch will listen or snoop the network for devices that want to receive messages and keep track of what ports they're on. So when a multicast message from the sender is received at the lean managed switch, it will only forward the message to devices that ask to receive those messages. The other devices that don't use the information will not be sent the messages. So for example, in the diagram on the left, messages coming into the network are sent to all devices. That is, even if the device does not want the message, it still receives them and reads them, taking up network bandwidth as well as processor time of the device. In the diagram on the right has IGM snooping enabled. The managed switch, represented by the rectangular blue boxes, only forwards the messages to the multicast addresses that need the information, helping to reduce traffic and improve network performance of the entire network. You may be wondering how a message is classified as multicast. Multicast communication used by Ethernet-based field buses are a group communication, and there are special IP addresses reserved for this type of communication. In this chart, you can see that IP addresses starting with 224 through 239 are designated as multicast. The Internet Engineering Task Force, or IETF, have set up this convention. So IGMP snooping monitors traffic with messages with these IP ranges and can map out what devices on the network request this information and what devices do not need the group information. So IGM snooping is a great tool to help improve network performance in more congested networks that need to use multicast messaging. And another way to help improve performance of your network is to prioritize critical devices on the network. So typically, networks operate on a best effort delivery basis, which means that all the data traffic per port has equal priority and equal chance of being delivered in a timely manner. This also means when congestion on the network occurs, all the data traffic per port has an equal chance of being dropped. But using a port priority feature, you can select specific network traffic and prioritize it according to its relative importance. Implementing port priority in your network makes network performance more predictable and bandwidth utilization more effective. In this screenshot, you can see that ports 3 and 4 on this 10-port switch have their priority set to high. Therefore, in the event there is too much traffic on the network, these two ports will have an increased chance that their data will be forwarded in a timely manner. Using a lean managed switch on your network can help prevent a network shutdown due to an installed media loop. When installing large networks or multiple switches, loops are a common user error and occur when two ports on a switch are connected to the same cable as shown in this diagram. The problem is caused when the switch in the loop sends out a message. The messages loop back to itself and are resent again and again, causing a broadcast traffic flooding. If this occurs on a traditional unmanaged switch, the switch will likely shut down along with the network. Lean managed switches utilize loop detection and send out a probe packet every few seconds and wait to receive the same packet at that port, which can quickly identify whether a loop is present. If so, the switch will shut down one of the ports in the loop to prevent traffic flooding. This information is saved in a system log, internal messages, and SNMP data for reviewing and troubleshooting. So enabling loop detection can help reduce the chance of a network shutdown due to an unintended loop. And perhaps one of the biggest differences between unmanaged and managed switches, including lean managed switches, is the ability to set up redundant networks. In certain application, ring redundancy is recommended, if not required, to ensure that the system can remain online even if a network issues occur. There are two major standardized ring technologies used in industrial network. It's ERPS, stands for Ethernet Ring Protection Switching, and RSTP, or Rapid Spanning Tree Protocol. Both technologies detect and repair and prevent loops, but the recovery times is a big difference between them. So rings are used to help increase the availability of a network. In these network strategies, a media loop is engineered into the network, and managed switches are used to block paths so that the ring will not cause a flooding event. In the event an Ethernet cable is damaged or disconnected, the ring technology will recognize the loss of a path and unblock the ports so that an alternative communication path is enabled. Choosing what technology to use, ERPS or RSTP, is typically determined by the complexity of the network and how fast the network must respond to a disconnected cable. Now, ring networks can be configured in many different ways. In this diagram, there are 3 ERPS rings that work together to increase network availability. I would also note that managed switches used in these types of applications should have the ability to be supplied by 2 power sources. In the event that one power source is damaged, the backup one will take over the responsibility of powering the switch. In this type of network, engineers can keep a system operating even if there's a failure of a cable or a power supply. So I hope this information has been valuable to you. We've talked about a lot of different things, and we know that today plant floor network security is very important, right? We've learned that it is recommended to use defense and depth strategies to help protect critical infrastructure, especially things like on a plant floor. And using managed switches, users can implement a layer to their defense and depth strategy in a very cost-effective manner. And there are many different approaches to plant floor network security. And also, if you're using managed switches, users can add security to the plant floor, plus they can take advantages of many of the features to help them improve network performance at the very same time. So I encourage you, if you haven't done so far, develop a strategy to help improve your plant floor network security today. I thank you for taking the time listening to this presentation, and I'm going to turn it back over to Mark.
Charlie, thanks a lot for that material. Before we get started with the formal Q&A, I have a few questions. For customers that are small to mid-sized companies, do they have a person dedicated to cybersecurity, or might alarming to the right person be enough?
Yeah, well, I think that's a good question. Obviously, it all depends on the size of the company and maybe exactly what they're manufacturing. But typically, I find like in smaller companies, they don't have a cybersecurity expert. And a lot of times that responsibility is going to fall on a controls engineer, especially for the plant floor. But I think controls engineers understand the threats that they, cybersecurity or cyber hackers can be to the manufacturing facility. So a lot of times, I think as controls engineers can implement different layers of defense, things like lean managed switches to help them, at least with their plant floor security.
So I noticed you had a checkbox configuration on some of those slides. That makes it a lot easier. Do the tools mentioned have documentation available, or is it pretty much plug and configure?
Yeah, I would say that most manufacturers of managed switches usually have a very thick manual, or you can download a very large PDF, and those documents usually provide a lot of information on, not just how to set up or configure some of these network features, but they kind of give you examples as well. So I think that's a great resource. It's just the manual itself, but also note that many companies also provide, um, like YouTube videos on how to do configuration, and they're usually broken down by specific functions. So I think you can find a lot of information online with videos, or you could refer to the manual.
And then network health might not only suffer from a cyber attack, there could be unintentional traffic flooding, right? Could you talk about that part again and how it relates to device configuration?
Yeah, sure. As I mentioned before, a lot of these lead managed switches will have something like loop detection built in, and loop detection or adding of a loop is an occurrence that happens quite a bit, and it usually just happens when you're adding new equipment to your system. And systems are usually more complex than the diagram I showed, where there are a couple of devices. Usually they're across several different control panels, or maybe across a campus. And so it is much more difficult in the field, right, to know if you really put a loop together. So that's typically when a unintentional loop is invoked or added to a system, when you add some equipment and maybe you plug in a switch and have a loop, even though you're not aware of it, right? That can occur.
Does port priorities relate to the use of zone designs with the network, or are they separate concepts?
Well, I gave an example of port prioritization, and that's really more geared for applications that may have some congestion or network congestion, maybe at certain times, during manufacturing, and that you want to make sure that your critical devices communication, keeps on going between those devices, and things that are maybe like a data log or something may not be as critical. So you want to deprioritize those. So I would say that's a different topic really than zoning. I mean, we talked earlier about using VLANs to separate networks and zone networks. So in the case of zoning Ethernet traffic, I would recommend using a VLAN.
And then for ring redundancy, could you have that for only the most critical area of your network rather than for the whole network?
Yeah, you sure could. As most people know, most people know, things get complicated quickly. So it's usually good to identify those critical, machines that need to communicate together, and then work out or plan out a ring redundancy, strategy just with, that equipment. And then your other equipment, you can keep on a kind of a standard point-to-point network. Usually those networks are very reliable anyway, but I definitely think it makes sense to have rings only where necessary.
Well, Charlie, thanks again for your expert presentation and these additional questions. And I'd invite the audience to join us for the live Q&A for those listening live. And you can participate in the live Q&A looking at your Zoom invite details and joining the session when prompted after reviewing the presentation. Thanks very much, and we'll see you over at the Q&A session.
All right, thank you.